Today let us discuss metallurgy. Metallurgy is a process of getting pure metal from the impure ore. You may get a doubt, why should you take an impure ore and then purify it? Because that is what is available in nature. A ore is available in nature along with impurities only after mining. And let us see what is a mineral. Mineral is a metal compound. Metal compound. You can even use the word for non-metals also. KCl is a mineral of chlorine. So, mineral is a metal or generally non-metal compound which is available under the earth, mines, that is mineral, metal compound. Ore is a mineral from which the metal can be extracted, profitably and cheaply. So, all ores are minerals, but all minerals are not ores. Look here. Minerals, a part of the minerals are ores. Ore is a mineral. Ore is a mineral from which the metal can be extracted profitably and cheaply. For example, sea water is a mineral for many. It may contain gold chloride also. But what happens when you start electrolyzing sea water, you will get 1 rupee worth gold after you spend 1 lakh rupees of electricity. So, there is gold in it, but you can't extract the gold in sea water profitably. So, sea water is a mineral but not an ore of gold. Now, metals are highly reactive. Metals are highly reactive. Therefore, if you keep a metal somewhere, it is converted to one of its oxides or sulfides. In open air, if you keep, metals are highly reactive, they don't keep quiet. They combine with oxygen forming oxides, and below the earth they combine with sulfur to form sulfides. So, most of the ores are either oxides or sulfides. So, metals exist in combined state only. They don't exist in their native state. Native means uncombined state. But there are very few metals which are available in their native state. Best example is gold. Gold, you can directly get gold from gold mines. Gold is there, it is not gold oxide that is present, it is gold. So, gold, platinum, silver to some extent are also available in native state. Okay? Some small quantities of platinum and silver also there in their uncombined state. All other metals, they exist only as metal compounds. And extraction of a metal from its metal compound is always, the chemical process is always reduction. Suppose you are getting aluminum from Al2O3, what is that you are doing? Al2O3 is bauxite or alumina, bauxite say. Okay, what are you doing from +3 to 0? So, you are reducing, this oxide is being reduced. So, it is very difficult. Metals, what they do is they lose electrons naturally. They lose electrons. This is a natural process. And the opposite process is very difficult. That is, making a metal ion take the electrons. For example, copper 2 is there. You can't give electrons to this copper 2. It doesn't take the electrons. Metal ions don't take electrons easily. So, you have to force them to take the electrons. So, broadly there are 3 steps in metallurgy. First step is concentration of the ore or ore dressing. In this step, you start with impure ore to pure ore. So you listen to this very frequently, very often, that concentration, purification, the term. But you should know who you are purifying. Here you are purifying the ore. First step, concentration of the ore, purification of the ore dressing. Impure ore to pure ore. You get impure ores from mining. After mining, whatever ore you get, you purify that. 1A, there is a step between 1 and 2. 1A, you make roasting, calcination and smelting. 2, this is called extraction of the metal. Extraction of the metal. So from pure ore to impure metal. Why should you get impure metal only? Even though you will try a very great deal, you can't get the metal in its 100% purity. So let us not focus on purity in this step itself. In a different step, we can actually purify the metal. Okay? First, getting the metal is important with say 90% purity, 95% purity. First, you get the metal, then you can slowly use the technique to purify. So third step. So in this step, ore means metal compound. Metal compound to metal means plus to 0, reduction. So the extraction of the metal, this is also called reduction techniques. There are several reduction techniques. Now 3, purification of the metal. Purification of the metal. This is also called refining the metal. Refining the metal. Where do you start? From impure metal to pure metal. So this is the starting point of the first step, ending point. Impure ore. So you must have heard impure many times. Here impurity is the ore, here impurity is the metal, don't get confused. Here if we are talking about aluminum, from red bauxite to alumina, impure ore to pure ore, like that. So in the first step also there are several questions. First step, hand picking is a very primitive technique, hand picking, but it's interesting. Depending on the gravity, you just pick a particular piece of ore into your hand. If it is heavy, you can say it is ore. If it is light, it is like a stone. Suppose ore and stones are present. Ore and stones, bricks, they are present. Depending on the gravity, depending on the density, what you do is you can separate. It's a primitive technique, hand picking. 2, electromagnetic separation. Electromagnetic separation. When can you employ this? When either the ore or the impurity is magnetic. So ore or impurity is magnetic. This you can encounter in cassiterite to tin. Cassiterite is an ore of tin, and during the extraction of tin you use electromagnetic separation. SnO2 is cassiterite, wolframite is the impurity, and wolframite is magnetic, and SnO2 is non-magnetic. Therefore, using an electromagnet, what you can do is you can separate. So what is important? When do you employ electromagnetic separation? Okay, there can be several examples, but in our syllabus they mention only tin. So during the extraction of tin, this phenomenon called electromagnetic separation occurs. There is another technique called hydraulic washing. Hydraulic washing. Washing the ore and impurity in a stream of water. Ore and impurity in a stream of water. Remember, only when the ore is heavier this is employed. Ore is heavier, impurities are lighter, because impurities will wash away. Okay, ore remains here in a stream of water. Hydraulic washing in a stream of water. So these three are rather less important techniques. So I don't use much time on them, but froth flotation is a wonderful process. Froth flotation. Froth flotation. Froth or foam or lather. foam. You know, or when you dissolve soap in water, you get foam. We are talking about that foam or froth or lather, flotation. This is used for sulfide ores only. Froth flotation is used only for sulfide ores. So, most of the ores I told you are either sulfides or oxides. We use this only for sulfide ores. Example, CuS is an impurity, PbS is the ore. Impurity, ore, galena. So, what is done is, the ore is powdered, small quantity of water is added, very small quantity of water is added, and whichever is more ionic will react with water. Ore is powdered and you will make only a paste, you don't add too much of water, small quantity. So, only the more ionic CuS absorbs water. PbS being more covalent, it doesn't absorb water. So, next small quantity of water is added, small quantity of water until you get only a paste, not a solution, a semi-solid. So, the small quantity is attracted by CuS and eucalyptus oil or pine oil is added. Eucalyptus oil or pine oil is added. That will be attracted by whoever is more covalent. So, PbS being more covalent, oil surrounds. O stands for oil. Since oil is surrounding this, now water cannot reach this place. So, we are making it oily, we are making PbS oily so that water does not touch. So, this is called preferential non-wettability, of ore to impurity. PbS is not wetted, means it is not surrounded by water because it is covalent, so, or because it is surrounded by oil. And now you use a substance ethyl xanthate, ethyl or methyl, sodium, potassium, ethyl xanthates. Xanthates, they act as emulsifying agent. What is an emulsifying agent? Which has two hands to attract both mass and charge. Water is polar and this xanthate is also it has got a polar end. So, polar attraction. This is non-polar attraction, this is van der Waals. So, what happens? Now, the PbS floats, you get it. The collection of these three is called the froth. You will find these three in the froth. So, froth contains water, ethyl xanthate and lead sulfide. So, what happens? When you add a lot of water, CuS goes down, PbS goes up. Air is circulated to create that foam. Aerators circulate air. So, this is all about froth flotation. Next, 1A, roasting. Why did I call it 1A? Why have I not taken it as 1, 2, 3, 4? I am not calling it as a second step because in this process 1A, the intention is sometimes purification of the ore and sometimes extraction also will take place. So, this is you can say is an intermediate step. Roasting, once again for sulfide ores only. Sulfide ores only. Roasting is there only for sulfide ores, not for oxides. The strong heating in oxygen is called roasting. What is the purpose? To convert sulfide to oxide. To convert a sulfide to oxide. Why should you do that? To convert sulfide to oxide so that this oxide can be reduced by coke easily. Perhaps you do not understand the phrase very easily. I will make you. So, zinc sulfide, you roast that, you are getting zinc oxide. And when you get zinc oxide, you take coke, carbon in the form of coke. Carbon is pure carbon, coke is pure carbon, and you heat very strongly, you get Zn plus CO. So, what is it I am doing? Sulfide is converted to oxide and only this oxide is reduced +2 to 0 from here. But why can't you do it directly Zns plus C? If you directly reduce, you get zinc and carbon disulfide, just as you may get CO or CO2 there. Just as you got CO2 there, why can't you get CS2? Yes, this is possible. So, here sulfide is converted to oxide and then reduced. This is called roasting. Why can't you do this directly? Carbon disulfide is formed, but this is an endothermic compound, unstable compound. Therefore, reaction becomes reversible. So, you are heating with the coke, you are getting zinc, and zinc is once again, so reversible reaction. So, but this is not reversible, this reaction, permanent, one way. So, what about roasting? Only 3 sentences, don't learn too many sentences. What about roasting? For sulfide ores only. What does it mean? It is not for oxide ores. Because oxide ores need not be roasted. The purpose is converting it to an oxide. For sulfide ores only. Then, strong heating in oxygen to convert a sulfide to an oxide so that the oxide can be reduced easily. Means sulfides cannot be reduced easily by coke. So, that one. Then, calcination. Calcination means getting a powder, something powder in the form of powder. Strong heating, be it in presence of oxygen or absence of oxygen, it makes no difference. Don't worry about whether oxygen is there, because in any case you are going to do that in a open container. Because what is the purpose? Strong heating to remove volatile gases. Volatile gases. For example, you heat calcium carbonate, not very easy, 1000 degrees, you get CaO and CO2. So, even assuming oxygen is there here, it makes no difference. Oxygen is not going to bring any change. So, CO2 escapes. So, strong heating to remove volatile gases, this is called calcination. Suppose you have CuSO4 5H2O, you heat that also, you get CuSO4 plus water escapes H2O, volatile, evaporates. So, this is called calcination. Third step in 1A. So, in the first step, we looked at hand picking, hydraulic washing, electromagnetic separation and froth rotation. 1A we have, step 1A we have roasting, calcination and smelting. We are still in 1A. Smelting means strong heating to melt. What is the purpose? You should melt. Strong heating to melt. That's all. Only heating. Okay. We add a substance called flux. Flux is added. What is the purpose of flux? It decreases the melting point. It decreases the melting point, and sometimes it may even remove the impurities. It is not the role of flux. The role of flux is not to remove impurities. Flux is a substance which helps melting. And simultaneously it may or may not remove impurities. That is not our prime goal. So, flux is a substance. So, suppose you have calcium oxide as an impurity. You know calcium oxide is basic. How do you know? Calcium oxide is basic. Where do you know this calcium oxide is basic? Metal oxide, basic. So, you use silicon dioxide, which is called flux, and this one is an acidic flux. Impurity is called gong or matrix, G-A-N-G, gong or matrix. This is acidic flux. So, matrix plus flux, what you get is CaSiO3. You get this is called slag. What is slag? A thick layer on the melt. A thick layer on the melt. Slag, like what you get when you heat milk, you get a thick layer, malai. So, calcium silicate is slag. So, what is this? Basic impurity, acidic flux, and vice versa. When silicon dioxide is impurity, you add CaO. So, this is called smelting. So, what is the important role of flux? It decreases the melting point, that's all. And sometimes by chance it may remove the impurities also, but that is not the sole purpose. So, now we have covered 1 and 1A. So, from impure ore to pure ore. we succeeded. 1A, roasting calcination means you have done half the job. Suppose you are taking calcium carbonate, you are converting to CaO. It's a big thing, you break it into two. So roasting, calcination, smelting. Now the last part, the second part is reduction techniques. Reduction techniques. Depending on what you use that name. For example, hydrogen reduction. What do you mean by hydrogen reduction? Use hydrogen as a reducing agent. WO3, wolframite, H2, perhaps you may get tungsten. So this is called hydrogen reduction. This is not important, I am just telling you hydrogen reduction. What is carbon reduction? You take carbon as a reducing agent. This is called carbon reduction. So what is most important? +2 to 0, positive to 0. So what is most important? Positive oxidation state to elemental state, 0 oxidation state. Any metal, this is what is required. So use any technique, but you give me the metal. Then, so hydrogen reduction, carbon reduction, there is somebody called HGS, cinnabar. Cinnabar, it is what? It is an ore of mercury, as you can see well, mercury. You just heat it. You get your mercury and sulfur. This is called thermal reduction. Heat and get, just heating and getting, thermal reduction. I am not doing anything else, I am just heating. The sulfide ion is giving electrons back to mercury, take your electrons and go. So simple, this is called thermal reduction. Cinnabar, thermal reduction. Now, alkali metals like Na, alkali metals, they cannot be extracted very easily. Getting NaCl to Na is next to impossible. Getting Na from NaCl is a very, very difficult task, which, okay, so they can be extracted. S block metals and aluminum can be extracted by electrolysis of their salts. You must take the help of electricity, electrolysis of their salts in molten state. No other technique is, you can't reduce them with carbon because they are very powerful reducing agents. They themselves are very powerful reducing agents. Don't imagine carbon reducing them. For example, NaCl plus carbon, heating, what happens? Nothing. Okay. Then NaCl thermal reduction, you heat NaCl alone. Will you get Na plus Cl? Are you joking? Impossible. What are you expecting to happen? What are you expecting to happen? By just heating, you are expecting chlorine to give the electron back. Okay, chlorine may give the electron back, chloride may give it back. But do you think Na plus will take it? He is a highly electropositive fellow. He will not take. It is like taking a 1 rupee given to the beggar back. I have given 1 rupee to a beggar, and if he gives that to me back, will I take? No. Highly electropositive. Highly electropositive. Once given, once for all given. It will not be taken back. But you have seen mercury ion. Okay, sulfide gives the electrons back to mercury, silently takes it back. Means it's not highly electropositive. It is not highly electropositive. So it can be done. So, and suppose aqueous NaCl solution, if you electrolyze aqueous NaCl solution, you get hydrogen and chlorine. You get hydrogen at cathode and chlorine because you have Na plus, Cl minus, H plus, OH minus. Between Na plus and H plus gets deposited. So you can't electrolyze aqueous NaCl. So what is it you should do? Molten NaCl. Molten means fused molten liquid state. Fused state, molten state, NaCl. You will have Na plus and Cl minus ions only. No H plus. If H plus is there, H plus will go to cathode. Now who will go to cathode? It is none other than Na plus will become Na. Now, so what is it? Hydrogen reduction, carbon reduction, thermal reduction, electrolytic reduction, and there is one other thing called Goldsmith's aluminothermy process, where aluminium is used as a reducing agent for Cr2O3, Fe2O3 and Mn3O4. This is called Goldsmith's aluminothermite process, thermite process. Thermite is a mixture of aluminium and Fe2O3. This is called thermite. So when they are heated, what happens? When they are strongly heated, you get Fe in molten state and you get Al2O3. So depending on the reducing agent, we are giving the name. What do you mean by thermal reduction? You just heat and get thermal reduction. Then carbon reduction, hydrogen reduction, aluminium reduction by aluminium. So it is the name of the reducing agent we give there. Now, most interesting reduction is self reduction. So electrolysis of molten salts. Where do you use electrolysis of molten salts? Only for S block and aluminium. So magnesium, aluminium, sodium, they are extracted by sodium, magnesium, aluminium. They belong to S block. They are all extracted by S block plus aluminium. Electrolysis of molten substances in their molten state, molten ores. So not aqueous. Self reduction means no outside reducing agent is needed. You just heat. For example, you heat PBS. Roasting. Roasting means you know what? Roasting means heating in oxygen. Purpose to convert PBS to PbO plus of course SO2. So what is it I have done? Galena being a sulfide ore, it is a sulfide ore. I have heated with oxygen, which is called roasting. What is the purpose of roasting? To convert sulfide to oxide. And now what happens is, this same PBS and PbO once again react PbO. This product, one of the products itself act as reducing agent. One of the products itself, now on heating you get 2Pb plus SO2, balance the equation according to your need. So what reducing agent I have used? Nothing. One of the products of roasting itself. I have not brought this, I have got this on this reaction. This is called self reduction. So you will see self reduction in carbon and lead. Reduction with coke in ZNO, Fe2O3, SnO2. So three metals, zinc, reduction with coke, or which is also called carbon reduction. It is called chemical reduction. It is called chemical reduction because you are using a chemical. Chemical reduction, carbon reduction, reduction with coke is there only in zinc, iron and tin. What about this? Copper and lead? Copper and lead, self reduction. So you should know in each and what are the steps involved. So galena to lead. Galena to lead. Galena is lead sulfide to lead. What are the steps involved? Anybody's guess? Sulfide ore, froth flotation. Sulfide ore, froth flotation, 1. Sulfide ore, roasting and self reduction. That's all. Self reduction. 3 steps. You get lead. So you should learn the steps involved in each process and with a reason. Why is froth flotation? Sulfide ores, froth flotation. Lead sulfide is made to float, froth flotation. Roasting, sulfide ores, roasting, self reduction. Next, there is one very interesting process which is called cyanide process. Cyanide process for silver and gold. AgCl plus impurities. It is called horn silver. It looks like horns of an animal. Horn silver. AgCl plus impurities. You treat that with a KCN solution. KCN solution. You know, this is horn silver is insoluble in water. Insoluble in water. It doesn't dissolve. But what happens when you dissolve that in KCN solution? In one class we discussed unexpected solubility is due to complex formation. So this Cn minus will react with Ag and you get a complex called AgCN2 minus dicyanoargentate 1. Dicyanoargentate 1. What is most important? This is a soluble complex. This is soluble and impurities are left behind. Impurities are precipitated. You can remove impurities. Now what you have is only AgCN2 minus. See how many things you have done? You have removed the impurities by, this is called leaching. Leaching. Leech is a marine animal which sticks to the skin and draws blood only, no flesh. Between flesh and blood, leech takes only blood, preferentially. So, between AgCl and impurities, this cyanide is reacting with Ag only, bringing Ag out. This is called leaching. Impurities are not touched. So, there are two things. Cn minus touches only this. So, removing this is called selective reaction. Reacting selectively, this selective reaction is called leaching. Leech is a marine animal which selectively sucks blood, no flesh. So, AgCN2 minus, now you add zinc. Now you add zinc. What happens? Zinc will displace silver and don't feel sorry for silver, that is what you want. So, you got ZnCN4, ZnCN4 2 minus, ZnCN4, so silver. So, that is how you get silver leaching. The same technique is employed even in red bauxite to alumina. What is alumina? Pure Al2O3. Red bauxite contains iron impurities. For example, Al2O3 plus Fe2O3. If some FeO is there, you roast it to convert that Fe2O3. If some FeO is already there, I am using NaOH. NaOH is a leach. It selectively reacts with only one of them. Which one? For that you have to use your intelligence. NaOH is a base. Ferric oxide, metal oxide, base. So this base will not react with base. These two don't react. But what about Al2O3? Al2O3 is amphoteric. Amphoteric means it reacts with acids, bases, whatnot. Amphoteric. Both acidic and basic. So, Fe2O3 is only basic. NaOH is basic. So, why am I using NaOH? So that this fellow reacts with only one of them selectively. You get NaAlO2. NaAlO2, molten state. Don't think this automatically, lot of heating is involved, You get NaAlO2 in molten state and Fe2O3 floats on that melt and that is removed. So, what is this called? Leaching, selective reaction. Further on, you add water to this, you get aluminum hydroxide and on strong heating you get Al2O3. This time this is pure and which is called alumina. And this NaOH process is called Bayer's process. If you use just Na2CO3 for the same purpose, it is called Hall's process. Bayer's process it is NaOH, Hall's process is Na2CO3. So, we have looked at the most important reduction techniques. What are they? Self-reduction in lead and copper. Carbon reduction in, chemical reduction in zinc, iron, tin. Electrolytic reduction for S block and aluminium, metals of S block and aluminium. Mainly we have sodium, magnesium only. Sodium, magnesium, aluminium. Extraction of sodium, magnesium, aluminium only we have. We don't have the extraction of all metals. Electrolytic reduction. Thermal reduction, cinnabar. Hydrogen reduction, tungsten. Aluminothermy process, aluminothermy. This is for Fe2O3, Cr2O3 plus 3 plus 3 plus 3 oxides, Mn3O4. So 1, 2, 3, 4, 5, 6 processes are there. The name given depends on what reducing agent you are using. And above all, most important one is cyanide process. Cyanide process both for gold and same process. Silver chloride plus impurities. Cyanide removes silver, forms a soluble complex, and therefore this is called hydrometallurgy. Why is it called hydrometallurgy? Because what is involved? Water, aqueous solution, solubility, solution, so many things are involved. Hydrometallurgy. Thermal means pyrometallurgy. Electrical metallurgy. So metallurgy can be divided into electrical metallurgy depending on what process you are employing. That's no big thing. Next, last step we have refining the metal. Refining the metal. Refining or purification of the metal. Now we have impure metal. How will you get pure metal? One, electrolytic refining. This is done for zinc, copper and aluminium. Impure metal is always used as anode. Means impure copper is anode, pure copper is cathode. Pure metal is cathode. And impurities, you will find the impurities as a part of anode mud, the dirt, anode mud. So, what is the electrolyte? Impure metal is anode, pure metal is cathode. Impurities you will find after the electrolysis in the anode mud. And what is the electrolyte? Electrolyte must be of same metal. Suppose you want to refine copper, what will you take? You take pure copper, cathode. Pure copper, cathode. Impure copper, anode. And what should be the electrolyte? Aqueous copper sulfate solution only. So it's copper, copper, copper everywhere. You must have learned this process in electrochemistry. What happens? During electrolysis, nothing happens. Impure copper jumps into solution, becomes copper 2 plus and goes here. Same copper atom becomes copper 2 plus and takes this, and electrons are sent via the cell. So there is no role played by this copper, this sulfate, this H plus. All those present in the electrolyte are spectators. Only what is this? Anode. Anodic copper undergoes oxidation. Anodic metal undergoes oxidation and goes to cathode. This is called one-man show. Electrons are given by this copper, electrons are taken by this copper. In general, NaCl, Cl minus gives electrons, Na plus takes electrons. When there are two species, one fellow will give electrons, the other fellow will take. At anode, somebody gives electrons, at cathode, somebody takes. Here, copper is the only one who is giving electrons and copper ions are the only one. So, it is called one-man army. So, electrolytic refining is very, very interesting. This is employed for zinc, aluminium and what is the rule? Impure metal is used as anode, electrolyte is the same and pure metal is cathode. What happens? If you take pure metal as cathode, pure copper, and impure copper slowly but steadily, from impure copper only copper comes, impurities are left behind. Impurities are left behind. You will be surprised, silver and gold are impurities when you refine copper. Silver and gold, we are calling them impurities. But yes, other than copper, anything that is impurity only. And the silver and gold you get as impurities in the anode mud, they cover the cost of electrolysis also. Okay, silver and gold are impurities. Electric bills can be paid with the silver and gold you get. Electrolytic refining. Polling. metal oxide is impurity. This is employed only when metal oxide is impurity. Cu plus CuO. You take that copper and cupric oxide, which is impurity. This is impurity. Impurity. Cu plus CuO, which is impurity. Molten state. Molten means very, very high temperature, thousands of degrees of temperature. You stir the mixture with green bamboo poles. That is why this is called poling. You stir the molten metal with green bamboo poles. What happens? That greenness, green leaves and all, they are called bushes and marshes. And what do you get? Marsh gas, methane. So green bamboo poles produce hydrocarbons, and the hydrocarbons act as reducing agents. What happens? CuO is impurity. CuO plus methane, assuming strong heating, you get Cu plus CO2 plus H2O, all of them vaporize. Heat, high temperature. So where do you get these hydrocarbons? The hydrocarbons, you get them from bamboo poles, green bamboo poles. Okay, that is called poling. There is another technique called cupellation. Cupellation. Cupel is a vessel made of bone ash. Cupel. A vessel made of bone ash. This is employed for silver and PbO. PbO is impurity. PbO is impurity, and this is called a litharge. So, in this cupellation, this bone ash surface absorbs PbO. Molten state, of course, you take molten state and PbO you will find at the surface and you get a silver block. Cupel is a vessel made of bone ash, and the walls are made of bone ash. Bone ash is a good adsorbent, and the impurity is adsorbed onto the surface, and after freezes, now it is in a molten state. When it freezes, you get silver block. Impurities are there in the walls. You invert the container, you get pure silver blocks. What happened to impurities? They are attracted to the surface, PbO. Now, cupellation. There is one other thing called vapor phase refining. Vapor phase refining, Mond's process for the purification of nickel. You take simply nickel with impurities. You heat that with carbon monoxide. At a low temperature, you get nickel tetracarbonyl and vapors. What is interesting? Impurities are left behind. You have nickel and impurities. Carbon monoxide is just running away with nickel, like an eagle running away with a snake. All others are left here. So you get vapors of NiCO4, and when you heat it back, you get your nickel and 4CO at low temperature, at a higher temperature. This is called pure nickel. So what is the principle? Nickel and impurities. I am sending CO. What is he doing? He is running away with it. NiCO4 vapors. And when you heat, you get your nickel. Impurities are left here only. Vapor phase refining. Then there is another technique called zone refining. Zone refining, you have metal and impurity. Metal plus impurity. You divide the metal rod into zones, different zones. This can be done only when you want metal in small quantities. You can't do this for tons and tons. Where you want the metal in the 100% purity, there are some metals where you can't take any chance. Even 1% impurity causes a great deal. You know the metals used in semiconductors, gallium, zirconium, etc. Okay, so metal plus impurity, you heat this part, you heat this zone 1. You heat zone 1. What happens? This part melts. This part melts. You move the burner. Now the burner, the heating element is at the second part. What happens? The second part starts melting and the first part starts freezing. So now this is liquid, this is solid. When the burner is moved like this part becomes liquid and this part becomes solid, and impurities are soluble more in the molten part. I don't know why I know, but I can't give you the reason. Impurities like molten part. Impurities like molten part. Therefore, the impurities are going here. Now, you heat the zone 3, impurities will come. Zone 4 means the impurities are coming behind you like rats behind a Pied Piper. So, when the impurities reach there, you cut that part. This is called zone refining. What is the principle? Impurities don't want to stay in solid part, they want to go to molten part. This is liquid, then it becomes freezing, so impurities move, melt. Molten part, molten part, molten part, molten part. Means they go behind the impurities like molten part. They will be moving along the molten part, along the burner till the end. So, these were some of the interesting techniques. What is it we discussed? Polling, cupellation, vapor phase refining, zone refining, most importantly electrolytic refining, one man show. Electrolytic refining, there are one or two minor parts. Chromatography, there is a technique called chromatography, and liquation, distillation, but these are the most important ones. Now let us look at questions, please. Question number 1. Which metal is generally found in native state? You have 4 options: copper, gold, aluminum and ferrum. You can never imagine iron to be existing in native state. Iron reacts with oxygen and gets rusted. Aluminum also Al2O3. Copper also as copper pyrites, etc. So, native means uncombined. So, gold is least reactive. It doesn't react with everybody. That is why gold is so valuable. If you keep gold there, unless thieves take it away, it remains gold forever. But other metals, they combine with all other elements in nature. So, gold is gold because gold remains gold forever. Gold is gold because gold remains gold forever. Nothing will happen to gold. Gold sits, it is like, it's inert, noble matter. It does not react with each and every one. Okay, it doesn't react with oxygen. It doesn't get tarnished. So, gold is the answer. Second question. Cinnabar is the ore containing, we already seen it, HGS. And how will you get mercury? Cinnabar. Just heat and get mercury. Thermal reduction. Next question. The function of flux during the smelting is to make the ore porous, to remove gong. I told you flux is somebody used to remove gong, and what you can say the main purpose is to decrease the melting point also. To facilitate reduction, flux doesn't do anything. Reduction of flux is nothing but acidic flux or basic flux. CaO is basic flux, SiO2 is acidic flux. They can't do any reduction or oxidation. So, to remove gong means gong or matrix or impurities, option number 2. Fourth question. Sulfide ores are generally concentrated by froth flotation. What about roasting? Roasting is not for concentration. Concentration of sulfide ores, froth flotation. But roasting, the purpose is not concentration. Roasting, the purpose is not purification. Roasting sulfide should be converted to oxide. Next. Electrolytic reduction process is used for the extraction of, wonderful question, alkali metals 1A, 2A and aluminium. I simply said S block plus aluminium. So, all the above. It's a very, very, very good question. Why do you need the help of electricity? Because they are powerful reducing agents themselves. NaCl on heating, it may at best give Na plus Cl minus, nothing further will happen. You heat this, on strong heating, it may vaporize. On further heating, Cl minus does not give the electron back or sodium does not take it. There are two things, neither chloride ion gives nor sodium ion takes. So, thermal reduction, all these things, chemical reduction not possible. You can do it only electrolytic reduction, means you use voltage to remove electron and make sodium take the electron. Electrolytic reduction. Next, Auto reduction process is used for, auto reduction means self reduction. I told you copper, lead, this is self reduction, and cinnabar also you can say, cinnabar also you can say self reduction only, auto reduction, because HGS, heat, you get Hg plus S. But with the PBS and all, you heat in presence of oxygen, you get PBO, and then that PBO reacts with PBS. So you can say self reduction is there, self auto reduction is there, mercury, copper, lead also you can say. Next, complex formation method is used for the extraction of zinc, silver, copper. You know where is the complex formed? Horn silver, AgCl plus impurities. AgCl plus impurities. What happens? AgCl plus impurities. You get AgCN2 minus. AgCN2 minus. AgCN2 minus. Okay, complex. When KCN solution, what is most important? KCN solution should be there. AgCN2 minus. So the answer is silver. Complex formation silver. Poling process we just have discussed. So when the metal oxide is impurity, when the metal oxide, so for the removal of Al2O3, you can't remove Al2O3 at all. Al2O3 you need a very, very difficult process. So Cu2O from Cu. Poling is employed only in copper, and that too, that was a very old technique. Nowadays nobody is using. Today we use electrolytic refining for most of the metals. Next question. Leaching is a process of, what did you do in leaching? In the case of bauxite, Al2O3, red bauxite plus Fe2O3, this is, you did that in the first step. What is that called? Concentration of the ore only. So concentration. Of the following metals, the one which cannot be obtained by electrolysis of aqueous solution of its salt is aqueous solution. Listen. Last question. NaCl on electrolysis gives what? NaCl on electrolysis gives what? What do you get at cathode? Gives what? No one can answer this question, because aqueous NaCl solution, you have Na plus and Cl minus and H plus and OH minus, you get hydrogen at cathode. So between sodium and hydrogen, hydrogen preferentially goes to cathode, and of course between Cl minus and OH minus, okay, so Cl2. So if you simply ask NaCl on electrolysis gives what, we can't answer. Moreover, molten NaCl, molten means no traces of Na plus, Cl minus, no what, no H plus, OH minus are not there, molten state. So now sodium and chlorine. So where is it possible? So in the case of, it is all okay. In the case of S block active metals, lithium to cesium, magnesium to barium, aluminum, all these three you can't employ. You can't employ electrolysis in solution. Electrolysis of solution, no. So alkali metals and other highly active metals cannot be extracted by the electrolysis of their salts in aqueous state. Aqueous state, no. Thermal reduction, heating, no. Chemical reduction, carbon reduction, no. They can be obtained only by the electrolysis of their substances in molten state where there is no trace of water. So the answer is magnesium. Now, since we have one or two moments, we just discuss one or two things. Van Orkel's process. Van Orkel process. Same as Mond's process. Similar to Mond's process. It is nothing but, what is that? Mond's process is also Mond's process. This is for titanium and zirconium. What is the principle involved in Mond's process and Van Orkel? Both of them, the principle is vapor phase refining. Vapor phase refining. So we purified nickel by Mond's process, titanium and zirconium, titanium or zirconium, anything, plus impurities. You heat that with iodine, 2I2, you get TiI4, impurities are left behind and you get vapors of TiI4. Vapors of TiI4 and ZrI4, zirconium iodide. So you get vapors of both TiI4 and ZrI4, titanium, zirconium. At low temperature, what is the temperature? You need not be particular about some temperature you get this. At a higher temperature. So what is most interesting? Here impurities are left behind, only titanium and zirconium are taken to air. Only titanium and zirconium went there. Impurities are left behind. So at higher temperature you get your titanium back, Ti plus 2I2, which is nothing but pure titanium. Okay? With this we end our class and tomorrow we will meet again with a different topic.